Good morning, everyone. I wish to thank the organizer for inviting me and for giving me the opportunity to be for the first time in this city, and also the opportunity to present some pieces of my work and of the work of several colleagues that were involved in the projects I will show you. Okay, so the title of the speech is From Slow to Fast, and we will be dealing with some special types of mass movements which are difficult to be defined. So especially we will be dealing with deep-seated gravitational deformations. But which is the scientific question? And actually, my scientific question has also technical implications. The question is, based on geological and geomorphological evidence and the help of numerical modeling, are we able to disentangle, to find, to detect all the predisposing factors, or some of them, which are related to the onset of secondary rapid landslides in the context of deep-seated gravitational deformations? And this is the first part of the question, whereas the technical, let's say, outcome is more related to mitigation measures. So if we are able to find predisposing factors, probably we will be able also to find some proper mitigation works. So let's try to answer this question, starting from, just a very simple definition. I'm here among colleagues who are all working on landslides, so there's no need to give a definition about deep-seated gravitational slope deformation, even if a lot of definitions have been given in the last decades. Actually, the terms rock flow and sucking, and on the other hand, the lateral spread, are the terms that are mostly used in research papers currently. In particular, I will be dealing with rock slope spreading and or lateral spreading, as you want to call them, no problem. And when I was preparing this presentation, I was looking for pictures and papers on this type of landslides, and the outcome was that most of these landslides occur in very nice areas. So it's also, these are also nice areas to work on. So the most used definitions are, on the one hand, block spreads by Cruden and Barnes, so movements involving a thick layer of rock overlying softer materials, or we can use the word lateral spread or rock spread when we are mostly focusing on the lateral expansion of these rock masses. And the same applies for rock slope spreading by Professor Angre, who especially focuses on quasi-horizontal stretching of this cap rock on top of weak materials which are outcropping at the bottom. Actually, from these nice locations, we will be focusing on specific and quite typical lateral spreading phenomena in the Apennines of Italy. So we are more or less in the Adriatic region, not outside the Adriatic region. And the model of the evolution of this lateral spreading in this area was proposed by Professor Pellegrini, who was my former professor. And in general, what we can see is that starting from a cap rock, which is coherent and almost intact, this cap rock starts to sink and to spread, ending in these conditions. So this is the situation of Sasso Simone, which is a slab of sandstones overlying clay shales at the bottom. And you see that all the features of lateral spread are visible in this picture. So you see trenches, you see some areas which are actually sliding in this direction, and you also see that the borders of the slabs are affected by other type of slope instability phenomena. So if we start from the general, let's say, condition, we could say, okay, what's the problem here? These are slow movements. And I thank Veronica for giving the introduction to the technique that was used, for example, in this area, in Malta, for measuring the displacements of a cap rock overlying clay shales in the city of Medina. So by PS, the colleagues from Florence were able to measure the displacement of some points. And you see that actually we can see some points which are almost stable, some of them which are displaying trends of movement, but we are every time in this field, so some millimeters per year. So actually this type of movement is an extremely slow movement. Another research work using PS analysis was by some colleagues, also by Stefano, who is sitting over there. And this is again in Malta. And you see that by the analysis of ERS and ENVISAT data set in all the coastal area of the northwestern coast of Malta, some points are showing movement. But again, we are in the field of extremely slow movement. If we focus, so if we have the possibility to use other monitoring techniques, like for example GPS, we can see that actually not in all the cases these movements are extremely slow. Like in this case, by GPS, again the colleagues from Padova and Trieste and Modena were able to measure movements in this area, again on the coastal, on the northwestern coast of Malta, which is affected by lateral spreading and block spreading. And again, the trend of movement is slow, but not so slow. So we are moving from millimeters to centimeters per year. So we are not in the extremely slow, let's say, class, but in the slow class. And this trend, in particular, is quite evident. So this trend is linear. So probably we are here monitoring the progressive evolution of this lateral spreading and or some secondary movements that are taking place at the boundaries of the slabs. And this is our focus. So what happens at the boundary? Frequently, and this is the engineering significance of the work, when you are dealing with the boundaries of slabs affected by lateral spreading, you can experience rapid movements. So the evolution is from extremely slow movement to fast movement. And this is for brittle fracturing, which is really, really difficult to be detected. Because also if you have monitoring systems, how can you deal with very instantaneous and very rapid detachment of blocks? So the idea is to go back and try to analyze which are the predisposing factors that are leading to this rapid evolution. So if you go back to literature, there are a number of possible causes that prepare slopes on the short to the long term, so preparatory factors. So one of the possible causes is the contrast, so the different rheology of the cap rock with respect to the soft rock at the bottom. Then some authors propose the overburden caused by the cap rock on soft overlying clays. Some authors deal with lateral erosion, so the removal of material at the borders, or to the presence of fractures in the cap rock. Recently, we have also worked on the role of groundwater hosted within the slab. So we actually try to find if there are evidence of these different preparatory factors with respect to our case study. So we selected a representative case study. So now we are here in Ljubljana. This is Bologna, which is not my home city, but my university is there. My home city is Modena, which is here. And San Leo is more or less here, so we are in the Adriatic region. And why we selected San Leo for trying to analyze preparatory factors? Because San Leo is expected to be the most beautiful city in Italy. So not in the world, but in Italy. And this is a sentence by a Nobel Prize, and he said that, okay, a fortress and 2 churches, it's enough. This is the most beautiful city in the world. So we have a spectacular location, we have cultural heritage, magic atmospheres, because there were famous people living in San Leo and also imprisoned in the castle. People are very nice in that part of Italy. There's good food, and of course, high landslide risk. These are the gates of the city, the ancient gates that were abandoned because this part of the cliff was destroyed by landslides. So they had to find another access to the city. So we searched for documents, as this is an historical area, and we found paintings and old pictures, which were compared with the, let's say, more or less present-day situation. And some parts of the rock slab were destroyed and completely shattered by large landslide events, like this part here and also this part here, mainly in the 17th century. And also during the Little Ice Age, a number of landslide events were recorded. But apart from historical landsliding, there were also very recent events. So this is again a painting from the 15th century. This is a picture of 2011, and this is a picture of 2014. So in the last 2 decades, 2 major landslide events affected the San Leo rock slab. The first was in 2006, and it affected the northern slope with a detachment of more or less 50,000 cubic meters of rock and the activation of an earth slide at the bottom. Whereas on February 2014, a larger rock toppling affected the northeastern sector of the cliff with a retrogression of the scarp in the order of 40 meters. And you see that actually some buildings were very near to the crown of the landslide. So these buildings were evacuated together with the school and the police station. So after this very big event, Emilia-Romagna region set a landslide risk assessment and mitigation plan, which we had the possibility to collaborate in. And if you want to have a look at some very nice videos, you can search for YouTube, and there are very nice videos and pictures about the landslide. So our task was to go back to the field, searching for evidence. So my focus was not on the mitigation plan. My focus was on understanding which could have been the possible causes of this switch from very slow movement to very rapid movement. And when we went back to the archives and to the field, we found some very, very nice pieces of evidence about some geological processes going on. In particular, at the base of the cliff, undermining was recognized. And some springs, both perennial and also ephemeral, were recognized, together with the piping processes at the bottom, sheet and rill erosion, and softening of all the clay shales at the bottom, together with some sort of pseudokarst dissolution features. This is a person for scale. You see that these are actually caves. And these are developing at the contact between the sandstones here and the clay shales here. Other very important pieces of evidence were found on top of the slab, because on top of the slab we had the opportunity to map open fractures. And you see that these open fractures are evident also in orthophotos. Due to the presence of these open fractures, rainfall, of course, can infiltrate. You have the onset of groundwater flow and related weathering processes. And of course, when the groundwater reaches the base of the cliff, you have softening and all the processes that were evident at the base, so the undermining. Consider that on pre-existing fractures, like this one, the big one here, wide oxidation films were present. So this means that the fractures were open even before the landslide. And we calculated that more or less the 55% of the scarp was composed by already existing fractures. So we tried to draw an hypothesis about the failure mechanism. So starting from a situation where you have a cap rock, so sandstones and calcarenitic rock masses, fractured, and clay shales at the bottom, and this is a sort of representative cross-section. We hypothesized that this pre-existing fracture was opening and propagating to the bottom, leading to a toppling of this rock block. Then the rock block was completely disgregated, and a sort of debris avalanche took place. This is a picture of the event taken just during this phase, so the debris avalanche phase. Okay, but this was an hypothesis because we didn't have any data about this possible evolution. So this is just a cartoon. So we tried to start from the geological model and to build numerical modeling using several data that we gained from the lab, from the field, and also by specific testing we did, in order to use numerical modeling as a tool to understand which can be the main factors influencing the evolution of the slope. So let's go back to the geological model. Again, we have the cap rock, limestone, calcarenites, and sandstones laying on clay shales. So geological mapping was performed in order to find the most important structural lineaments. But we had also the possibility to use some other easier techniques, because you see that doing engineering geological surveys at the base of the slab is not really convenient. So we used photogrammetry and laser scanner in order to build the 3D model of the slab. And to gain some information about the orientation, the spacing, and all the features of discontinuities. The data from photogrammetry and terrestrial laser scanner were used for, let's say, classification of the joint sets using the Coltop software. And this helped to identify the most fractured area in the slab, and also to do a quite simple kinematic analysis of the possible sliding mechanisms with respect to the rock mass. We also collected some samples to characterize the intact rock and to have an idea about the rock mass properties, and this was done in the lab. And at the same time, we tried to characterize the scaly clays at the bottom, and this is really a difficult task, because these scaly clays are very difficult to be sampled, and after sampling, these materials are very difficult to be tested in the lab. Anyhow, we thought that this was a quite important part of the story, because if you start from scaly clays, and if you soften them, you will end up with some specific phenomena like swelling and shrinkage, which can be important in the evolution of the phenomena. So actually, we found that these materials have a very high degree of activity, so they can undergo swelling and shrinkage, and this was confirmed also by odometer tests. Then we focused on groundwater, because our idea was that groundwater had a very important role in the story. And this because being the rock mass fractured, and when groundwater builds inside the slab, also with the presence of springs, you can have some processes, some geological and geomorphological processes occurring at the base, which can drive the evolution of the whole slab. So we did also some tests in the field in order to gain data about the permeability of the rock mass and all the features of the aquifer, like storativity. We did an analysis of the rainfall and the climatic data, and we did some monitoring on springs, on piezometers, and also some field tests to have an idea about the permeability. And this allowed the hydrogeological model to be built. So the slab is behaving like an aquifer, and groundwater is hosted within the aquifer. And we had also the opportunity to calibrate the model by using the springs that were mapped in the field, and to have an idea about the general behavior of the aquifer at the slab scale. So by using all these pieces of information, we did some numerical modeling exercises using different types of softwares, both on 2D and also 3D, and with discontinuous and continuous approaches. Today I'm showing just this part, so the modeling exercise done with phase 2, which is a 2D finite element continuous code that we used to simulate the effects of some possible predisposing factors. On the one hand, the softening of the clay-shale layer at the base of the cliff, the undermining, so this geometrical feature, the presence of main discontinuities within the rock mass, and also the role of groundwater. So we back-analyzed the 2014 event on this cross-section. And this is the setup of the 2D model. You see the slab, consider that this is a continuum code. So we introduced the discontinuity deterministically, whereas we assigned to the rock slab a sort of set of parameters that we obtained from back analysis. Whereas we used the parameters from the lab to characterize the clay shales. So the two main parts are, on the one hand, the analysis of the behavior of this softened clay shale layer at the bottom, and on the other hand, the progressive removal of clay shale slices at the bottom. These are some results. So if we start, if we consider the presence of a 5-meter thick clay shale layer at the bottom of the slab, we can try to test an extension of 10 meters, 25 meters, 50 meters, and an extension that goes under the whole slab. And you see that if you extend the clay shale layer within the rock mass, some sort of instability starts to occur. These are points that are at failure. On the other hand, if you keep the constant, the extension of the clay shale layer, you can try to lower the properties of the clay shales. And when you lower the properties, you see that, again, some sort of instability occur at the boundary of the slab. The results are more or less coherent as order of magnitude with the results we obtained from the lab. But you will see the shape of the scarp that we obtain by considering these two possible predisposing factors is not resembling to the real one. In fact, the best results were obtained by removing slices of clay shales. So if you build by excavation in the model the undermining, you obtain the propagation backward of the scarp like actually we had in reality. So this is the best result we obtained by using the main discontinuity introduced deterministically and by removing progressively slices of clay shales at the bottom. This is the strength reduction factor, which sounds like the safety factor, and you see that we have instability when the undermining reaches more or less 22 meters. The estimated extent of the caves at the base of the San Leo slab is in this order of magnitude. Of course, no one went in, but by looking at the extension, people walking around and making pictures said that more or less the extension could have been around 20 meters. So this sounds good. And what about the main discontinuity? As I told you, it is important to consider also the presence of the main discontinuity, which is this one, because if you don't introduce the discontinuity in the model, then you end up with a shape of the scarp which is not consistent with the real one. So we need undermining and we need the discontinuity. And what about groundwater? If you add groundwater, actually you don't have the onset of the landslide. So this means that the increase of groundwater before the event was not really a triggering factor. On the other hand, if you consider the load, the possible load of water inside the main discontinuity, which is big enough, you have the propagation of the fracture, which seems to tell us that probably also the load of the water within the main discontinuity could play a role. But what I like the most is this. If you go backward, you find this area which is in tension. So this means that you have the creation of fracturing at the back of the main scarp. And if you look at a quite old picture, this one, which dates back to the 60s, you see that some fractures are evident. And in particular, let's try to have a look. So this is the scarp in the 60s. This is the house, and this is a small house. The small house is here. And you see that this is the scarp of the 2014 landslide, which is actually this one. So the discontinuities was there, and look, there are other open discontinuities, which are the ones that we were mapping. So this means that our model tells us that when you have these events, you have also the preparation of the next one. So we have this circle of processes. We have groundwater flow in the slab. We have chemical and physical processes which are promoting weathering at the base in the clay shales. And then you have undermining of the slab. After this, you have the development of tensile stresses in the upper part, and then the onset of large-scale slope instability. So from slow processes, you end up with rapid processes. And this is a circle. So this happens in a sort of circular process. So let's try to answer to the second part of the question, so the technical part. What can we do in order to, let's say, solve or at least try to reduce the risk for the city? These are projects that are dated back to some decades ago, whereas this is ongoing. So they are doing extensive bolting across the main discontinuities in the rock mass. On the other hand, they are building a pile-founded retaining wall in headwater catchments and some check dams to, let's say, control small rivers. Besides this, they are also doing, they also have monitoring systems across the main discontinuities, and these are the data they are collecting. The data are telling almost nothing, so it's just seasonal movement, no trends. And also they have two buildings which are still evacuated, and they have a civil protection plan because these instruments are also, have also a threshold for alerting purposes. But, I mean, are there other approaches? From my point of view, yes. Because based on the evidence, so on geological and geomorphological evidence, we have an idea about the processes. So we have to tackle the processes. Bolting, at least from my point of view, I'm just an engineering geologist, is not effective. So why we don't go back to the circle and try to say, okay, why don't we think about drainage? Why don't we work to reduce the undermining? And to reduce the undermining, we could think about grouting the main discontinuities. This is done for civil infrastructures like dams. Why don't we do it also for rock slabs? So the idea to go on with this research is to improve our definition of groundwater within the rock mass. We want to go back and measure and to map and measure the discharge of the main springs in order to see where undermining is accelerated. And also we want to measure how long it takes to have the caves developing. So we want to measure the erosion rate. And this is a Slovenian colleague trying to have a look at what happens at the base of the San Leo rock mass. So there are several papers that you can eventually download, or I have copies if you want, but I have to say thanks to a lot of people, you see, because this is just a very, very small part of a huge amount of work we have been doing in this area since some years. And the data set was made available by the Emilia-Romagna region, and you see that this was the situation, but now this is no longer there. Okay, thank you. Thank you.